Here's a brief introduction to scalar line integrals. I'm going to do it with a physical example. Scalar line integral is a generalization of arc length where we take any curve and we integrate a function along it. We add up the values of a function along the curve, basically. When would we want to do that? Well, for example, suppose we have a wire that's a quarter circle. Let's say we set up our coordinates. Let's say it has radius 2. We set up our coordinates so it's exactly the first quadrant part of a circle. And if we wanted to find the length of the wire, that's a standard calculation. It's the integral over that curve, let's call it C, ds. The idea is you break it up into tiny little bits, calculate the length of each little bit ds, and you add those up. And remember how we did that with an explicit parameterization. You use the fact that a little bit of distance is rate times a little bit of time, and the rate is the speed, which is r prime of t dt. Okay, but now we want to go beyond that. What if we want to find the mass? Suppose it has a variable density. So this guy has a variable density, and I want to find the mass of the thing. Okay, so to be simple, let's say the density, and the book uses rho, but you really should use lambda for linear density. It's a Greek L. And we already use rho for our spherical coordinates anyway. Let's suppose this is just proportional to the distance from the y-axis, kx. Now it's a little unrealistic because it's going to go to 0 here, but I want the things to be simple. Okay. Now, how are we going to do that? Okay, it's still divide and conquer. The total mass is the sum of all the little bits of mass. Now, if I were being really careful, and the book tends to be careful about this, I would first set it up as an approximate sum, a Riemann sum, with a sigma, and then I would let n go to infinity. But you get the right answer pretty much almost every time by thinking about it this way. We're going to take a little bit of length, a little bit of the curve, and we're going to find the mass of that guy. And then we're going to add all those up. So now we just figure out what's the mass. Oh, that's the density times the little bit of length of the curve. That's what linear density means, that it's how much dm over ds. Okay, and so in this case, it's going to be kx ds. So now we've got a situation where we've got a function that's not just the function 1 that we were integrating here, and we want to integrate that over the curve. Take all the little bits of the curve, calculate the little length times this number, and then add those up. And then the rest of it is very much like this process. We're just going to be, in fact, let's put it up here. That's going to be the integral from whatever start to whatever end of our density function, and we're going to have to express that as t in terms of t, times the speed factor times dt. Okay, well that brings up, we haven't parameterized this curve yet. Oh, well we can do that. X equals 2 cos t, y equals 2 sine t, and t is going to go from 0 to pi over 2. Okay. So now we're ready to go. This is 0 to pi over 2. It's going to be k cosine t. Ooh, 2k cosine t, because x is 2 cosine t. Let's not forget that 2. We're going to need the speed in a second. Okay, so dt. So, okay, we have to do the speed. I think I'm done with this. Okay. But as usual, the velocity is just x prime, y prime, is just minus 2 sine t, 2 cosine t, and we just need the magnitude of that. And sine squared plus cosine squared is 1, the square root all gives you 2. That's really a very standard calculation, that the whole purpose of cosine t, sine t parameterization of a circle is to have unit speed in the usual case. If I want to go twice as far on twice as big a circle in the same amount of time, our standard amount of time to go around, it's going to have speed too. So happily, this guy is very, very simple in this case. It's just 2. And so this is a very simple integral to do. And so you get 4k integral cosine t from 0 to pi over 2. That's easily done to be 1. So you get 4k. Okay. Even another kind of thing you could do with the same technology is you could get, for example, the x moment about the x-axis. Remember, that's the integral of, you take the y values, you look at not only how big this little chunk is, but also how far from the x-axis it is, and you add those all up. The purpose you might be doing that for is if you divide that answer by m, you get the y-coordinate of the center of mass. Let me just put that right here. mx over m is y bar. That's why you might be doing it. And what's the formula? It's just going to be add up all the little bits of mass times where they are. That's always a formula for this kind of moment. And we just did all the other stuff. So that's just going to be integral a to b of y times lambda, which in this case is our kx, times ds. And you just put that in terms of t, put that in terms of t. This is already in terms of t. We got the calculation already. This is 0 to pi over 2. You could get that as well. I won't finish that off just to make the video shorter. But you can see that there are situations where we're going to have this process of integrating, just to sum it all up here, integrating over some curve, not just ds to get the arc length, but some f ds. The process is very, very, very much like the arc length process, though. So that's a scalar line integral. It turns out vector line integrals are more interesting, but that's a different video.